Okay, here we are back at energy. I'm not sure exactly when it cut me off, but we're talking about energy sources. Energy sources are places that we use for the energy that we use to run all the stuff that we use in our lives. Primarily, we think of electricity, but of course, we also have gasoline engines. A lot of things run on gasoline, and there are other types of energy. But when we talk about energy sources, we're really talking about where do we get the energy from. And so we talk about oil and gas and natural gas. Um, a lot of these were considered waste products. And at one time, oil oozed out of the ground. It was kind of a tarry mess, and it actually brought down the value of the land because you had these tar pitty things on your land. Natural gas for a long time was just burned off because there was no way to capture a gas and pressure and liquefy it, which is the way they transport it now. But so for a long time, it was just burned off and flared off, and it still may be if it's not enough or to make it useful. But at any rate, hydroelectric is dams, and when you put in a basically we're using what kind of energy in a dam? Basically, we're talking about gravitational potential because we put a dam in, and it builds up water, which is higher behind the dam, and then the gravity pulls it through, and as it goes through, it turns the turbine, which turns magnets, which creates electricity. Okay, so hydroelectric is an important type of energy as well. Um, Geothermal. Geo means earth. Thermal has to do with heat. There are places where there are heat down in the ground in the rocks. We can, either naturally occurs or we can pump water down there. It hits the hot rock. It produces steam. Once again, as that steam comes up, we can use it to turn a turbine. Uh, Not a very big production of electricity, but and only limited to those areas where you have access to hot rocks under the surface, but very limited. But it works good. It can work in small circumstances. Wind, which is becoming a bigger one. You've seen all the windmills going up. They're using to generate electricity. One of the problems with wind was originally you're putting these up out where there were no power generation before, and so they're having to build a lot of power lines to service these areas, and so there's a lot of expense to that. But wind is definitely here to stay. It's still not probably the major thing. We're still mostly depending on oil and gas, natural gas, and coal. Coal is one of the big ones, um, also for electricity, um, and of course nuclear energy. Uh, Nearest one we have to here is Glen Rose. Has the Comanche power plant, and at one time they were trying to expand that, but I don't know. There's a lot of resistance to people using nuclear energy, but these are all sources of energy that we use in our lives, and like I said, most of these are used primarily. We're thinking in terms of using them to generate electricity because everything from our cell phones on down uses electricity. All right. And while we're talking about work, we need to talk about machines. Sometimes they're called simple machines. Okay. And if you put several of these simple machines together, then you can call it a compound machine. And we don't think about these machines and not as these individual ones, but they are in almost everything. If you take apart even electronics and various things, CD players, whatever, a lot of your stuff, you will find inside it, you will find a lot of these simple machines there. But we kind of take it for granted because we don't see these simple machines. But there are six types of simple machines. There are levers. All right, levers have some sort of fulcrum in the middle, and you have a force pushing one direction and lifting a weight on another direction, and they rotate around this fulcrum in the middle. Now, if you think about this fulcrum, I made it circular. You have two other type of machines that are considered kind of related to that. Would be considered a type of lever. Okay, one is a wheel and axle. This is a bicycle thing. And if you drew a line straight through the middle, you could think of it rotating around here in the middle of the cog where you uh, turn the gears here. And that would be so it would be a force going one direction, lifting on the other side. That would be like a circular lever, but we would call that a wheel and axle. Okay, so wheel and axle would be that. Another example of a circular lever would be a pulley. Same thing once again. If you look at the pulley up close, you think about it, rotating around that middle being the fulcrum, you force on one side, lifting up on the other side. So once again, kind of a circular lever. But basically, so you have a lever, wheel and axle with any kind of gears would involve that. A screwdriver, you turn the handle, which turns a shaft, which turns the screw. So all of those would be examples of types of levers, but we would break that down into wheel and axle, and which would be those that I just described, and then pulleys would be over here. Okay. Now for other example over here, we have inclined planes, and I did not download that. But basically, an inclined plane would be a raft. Just a second, let me get one. There we go. Now we have an inclined plane. An inclined plane, basically a ramp. A handicapped ramp would be an example. On ramp onto a highway would be an example. Any kind of slope surface that allows us to get up somewhere easier with at least less force that we have to expend to get up there. All right. Now, some specialized cases of one of those is any kind of sharp edge, knife, scissors, etc., etc. If you look at the edge, it would get very thin at the end and it gets wider as you go out. So it would kind of be like that. Now, also in line with that would be a wedge. Okay, a wedge or a knife are basically the same thing. If you think about it, you look at the wedge here, it's very sharp right there, pointy, and you move it through something to split it in half. So knives would be an example of wedges and so forth. And those would be a type of inclined plane. And just that instead of slanting on one side, they slant on the other side and come to a point. So if it's a wedge, like a knife or this wedge in the wood, they would be like two inclined planes put together to make a point. All right. Now, if you took that same inclined plane like here and you wrapped it around a cylinder, then you would have a screw or a bolt, either one, the threads on a screw or a bolt. And basically, this is an inclined plane that's been wrapped around the screw. Okay. In this case, instead of something going up the inclined plane, you're thinking you're putting the screw in there. As it pushes into the wood, you could think of it as pulling the wood up, and sometimes you actually put a screw in something and it pulls the wood to the screw. But at any rate, it does basically the same function. So this is an inclined plane. These are the 6 types of simple machines. And while we say, oh, I don't use like a seesaw type thing, but you do use levers all the time. Your arm, for example, is a lever. Okay, it's attached at one end. That's the fulcrum, like your elbow would be a fulcrum. And then you would have muscles attached to your arm that would pull on it and pull up your arm and so forth. So actually these machines are everywhere. We just may not recognize them for what they are. Now the question is, why do we have all these machines? Why are they so important? Well, because machines are used to help us do work. Now this is very important. Machines do not change the amount of work it takes to do something. Okay. Sometimes people may say it makes it easier so you do less work, but that's not possible, to be honest. You can't do less work with a machine. If you're moving a certain object that has a certain weight, a certain distance, the amount of work is going to stay the same regardless of whether you use a machine or not. Okay, they don't change the amount of work, but they do some other things. For example, on the pulley over here, they allow us to change the direction of force. Okay, it takes just as much force to pull on here to lift this as it would to pick it up. However, the difference is now we can use our weight and gravity. If you were to jump off the ground, his whole weight would pull down on this, and that would make it come down very quickly. So that would be it makes it a lot easier because now we're working with gravity. Whereas when we pick it up, we're working against gravity. We're going against gravity. And so by changing the direction of the force, the pulley like this would be very helpful. Okay. Now, the other thing that it may help us to do is that it decreases the amount of force. And so in terms of us, we think, oh, I'm doing less work. Well, really what we're not saying, you're not doing less work, but you're having to put less force in it. Okay. But if the amount of work is the same, we just said machines can't change the amount of work. If I use this pulley system like this guy's here using the lift, it's going to use less force. But if the work is the same, the only way it can stay the same is if the distance increases. So in other words, for this bag here to go from here to here, he might have to pull rope he would have a pile of rope that might be twice that long. So he's having to exert that less force for a greater distance of rope, and he's going to have to pull on the rope a lot farther than the bag actually moves up. And same thing is true of all pulley systems. You can have 3, 4, however many pulleys you want put together. For example, there's block and tackles that use to lift engines out of a car. Why? Because it has enough pulleys that you don't have to use much force, but you're going to have to pull a lot of rope, a lot of distance, exert that force for a lot of distance. Think about the inclined plane. It's the same thing as lifting it up from here to here, but you only have to lift it a short distance. Here you have less force, so it's easier, but you have to go a lot farther to get up to the same height as you would if you just went straight up here. So that's kind of the trade-off with machines, is that it's less work for us, less hard on us, because we put a lower force into it, but then you have to increase the distance that you pull. A lot of machines do that. Now there are some machines, like a broom, where it's actually harder to use a broom with a handle than it would be if you were just to reach down at the bottom and move the broom at the bottom. But in this case, it multiplies the distance that is covered. All right, so if we were sweeping with a broom, even though it may actually use more energy, it will make the broom cover a bigger area. And if you're sweeping, and I know if I'm sweeping, I want to get done as soon as I can, so I appreciate that it covers a bigger area. Also, even though it actually increases the amount of force I have to use up here, it's such a small amount of force to move a broom that it's not that big a deal. Now, notice there are 2 types of work being done on a machine. All right. If I'm pushing, let's just use this guy up here. If I'm pushing down on this end, I'm exerting a force, and it's making this go a certain distance. This is called the work input. I'm putting it into the machine. On the other side, the rock is, or bag or whatever, is moving a distance because it has a force exerted on it. This force times distance is equal to the work output. So we have work input and work output. Work input is always more than work output, because some of our force and energy we're putting in here gets wasted from friction and rubbing in here. So you always get less output than you put in. Okay, and that's called the efficiency of the machine. The efficiency is equal to the work done, or the work output divided by the work input times 100 to get a percent. And ideally, a perfect machine would be 100% efficient. We put this much work in, we get this much work out, or even more work out than we get in. But that's impossible. You can never have more than 100. And usually it's always going to be less than 100, because it will always be less than 100, because you're always losing some of your energy work that you put in to friction and so forth, and it doesn't get transferred to the object you're trying to move. And so efficiency is less than 100%. And it's just the work output compared to the work input. And you're never going to get as much out of the machine as you put into it. People have always looked for a perpetual motion machine or an ideal machine, which would be 100% efficient, but it just isn't possible. And going back to what we talked about earlier with a car, about half the energy is just wasted on friction of the moving motor parts and so forth. A lot of the gas doesn't get burned. They put a catalytic converter. It's just a thing on the tailpipe. As the gas fumes go through, it has platinum and some other enzymes that burn that gas as it goes through. Now, that does not help the efficiency of your car, because that heat's not being used to power your engine. It's already gone through the engine, it's going out the exhaust. But and trying to burn that. So if you wanted to make cars more efficient, one, you can make them burn all the gasoline. You could try to reduce the friction somehow. I mean, always use oil and so forth to reduce the friction, but it's something to do even less, where there's even less friction. Then you might make the machine more efficient. But efficiencies can be very low, less than 50% or so, like that for your car. So if you want to make a machine better, you try to make it as efficient as you can. All right, the last thing before we finish up, I want to think about sources of energy. We talked about coal, oil, gas, and so forth. Someone says that if Dimwit says that all sources of energy are solar. And the question is that true or false? And we'll talk about that hopefully when we come back to class time. Certainly if someone reminds me to go over that. But he says that all sources of energy are solar. Is that true or false? All right. See you in class.